All right, in this video today, we're going to talk about lesson 12.5, which is how to calculate the curvature of a vector function. So you can see two curves that I've got here. First, I want to just point out that the idea of curvature comes from the idea that you should, kind of the forces you feel going around a tighter curve versus kind of a not as tight curve. And we define curvature to be the rate of change of the tangent vector. How fast is the tangent vector kind of changing as we go around the curve, which is why this formula right here, K or kappa, is equal to, this is our curvature kind of constant, the rate of change of the tangent vector with respect to the change in arc length. It shouldn't matter when we are on the curve, it should just matter where we are on the curve. So over here, if you look at this example, the curvature should be greater for P than it is for Q right here. So we should have a greater curvature where the turn is tight versus where it's more of a loose, kind of like slow curve, okay? So this formula right here is really only useful if T, our vector function, is already parameterized in terms of the arc length, which is not always true, okay? Also note that these are not absolute value signs, these are the magnitude. So curvature will be a number, okay? Curvature is also going to be inversely proportional to the radius if we made like a little circle right here. As the smaller, and we think of that as curvature should be inversely proportional to the radius of some circle. If I let me draw a little circle over here. Okay, like this is my radius. The curvature kind of representing the curvature at that point, because the smaller the circle is, okay, so the smaller the radius is, the greater the curvature should be. Okay, so it's kind of an inverse relationship right here. But again, this is the formula we might see most often, but parameterizing things in terms of arc length is not always convenient. Okay, so we can transform this into a more useful formula. So if we start with the rate of change of the tangent vector with respect to arc length, okay, I messed up a little bit on the key here. So this should be, if you want to fix this in your notes, the derivative of the tangent vector with respect to time, okay? So kind of just thinking about fractions here, you can see how this would be equal to this. The derivative of the tangent vector with respect to time over the derivative of the arc length with respect to time. But when we were talking about arc length, remember we had our arc length formula bs equals the integral from some initial point to t of the magnitude of r prime of u, du. So if I take the derivative of the arc length with respect to time, that's just going to be the magnitude, make sure my vectors are consistent, of the derivative of r in terms of time. Okay, that's our second fundamental theorem of calculus there from BC. So this helps me then think about the next step in my formula, because I can say that this is also equal to this, okay, dr dt, which is then just t prime over r prime. And that's a much more useful formula. And that is, again, the magnitude of that. Okay, so let's do an example together using that formula. Okay, so example 1 says, find the curvature of this vector function, 2 sine t, 5t, 2 cosine t. And hopefully you're starting to recognize that as a helix, okay? We can think about it in the xz plane. We're gonna get some kind of circle. So it's gonna be a helix with the y-axis as its center. Okay, so if you just wanna just make a note of that. All right. Then, if we're going to use this formula up here, we're going to need a number of things from here. So I'm going to find r prime of t first. That is going to be 2 cosine t, 5, and negative 2 sine t. Okay, then I'm going to need to find the magnitude, okay, of the derivative. Remember, that's a square root function, so it's going to be 4 cosine squared t plus 25 plus 4 sine squared t. And if I use my trig identities, I'm going to get the square root of 4 plus 25, which is the square root of 29. All right, so we've got our magnitude. That means that the unit tangent vector, which I will need, because I'm going to need to take the derivative of it up here. I need it in general. Okay, will be 1 over the square root of 29 times 2 cosine t 5 negative 2 sine t. Okay, and then I'm going to want to take the derivative of that. Okay, well, I can use kind of my constant rule that I did for derivatives and leave this on the outside. So 1 over square root of 29, then negative 2 sine t, 0, and negative 2 cosine t. All right. And finally, oh, we're almost there, okay? Because I'm gonna need the magnitude of that divided by the magnitude of r prime, which I already found here is the square root of 29. So the magnitude of my unit tangent vector will be, and you can include this in here or you can leave it outside. Either way, I'll include it just for the heck of it. I'm gonna get 4 sine squared t, okay, plus 0, plus 4 cosine squared t over 29. All right, so once again, I'm gonna get that square root of 29 in the denominator, but in the numerator, I'm gonna get the square root of 4. So I'll get 2 over square root of 29. Okay, and then we're gonna put it all together. My formula for curvature, and I'm sorry if you can hear my dogs in the background, curvature is going to be equal to the magnitude of t prime of t over the magnitude of r prime of t. Okay, if I put those together, I'm gonna get 2 over the square root of 29 divided by the square root of 29, which is the same as 2 over 29. Okay, so notice that this curvature, special note, is not dependent on time. Okay, and I want you to think about why that might be. And it's specifically because this is a circular helix. So if we're going around the same circle, just moving up in space versus down in space, it should be the same curvature at every point, okay? When you do the next example, you should find the same thing because we've got another circle here. But I'll leave that example for you guys to do. It'll be filled in on the filled notes. Okay. Okay, oops, looks like my pages are out of order here. Oh, I just printed it double-sided and I forgot. Way to save paper. Okay. All right, what is this geometric figure? This is exactly what I was just saying. Both of those examples should be a circle. And so since the turning of a circle, it should be same at every point on the curve. This is a special property, which leads us to the fact that the radius of the circle is 1 divided by the curvature. That was the exact ratio I was talking about earlier, that the curvature is 1 divided by the radius of the circle. Okay, we can actually create a circle that will represent that, okay, called the osculating circle. Again, radius r equals 1 over the curvature. And we can make a circle for any curve. Okay, think about this kind of circle rolling along a curve. Okay, so, all right, let's do another example, okay? This will be really short because I want you to notice something. When we find the curvature of this equation, okay, well, 4 cosine plus 4 sine, you should automatically recognize that this is a circle, okay? And if you need a reminder, a circle would be the equation r of t equals A cosine T I plus A sine T J. Okay, and A have to be the exact same in order for it to be a circle. That makes sense? So A is radius. So in our example that we have here, 4, so the R radius is 4. And if we use this formula right here, our curvature, and notice I'm trying to make a nice little curly K, so it's kappa and not just like regular K. Try to do that in your notes just to a little differentiate. You can do a better kappa if you would like. I'm just being a little lazy. So the curvature should be 1 over the radius, 1/4. And it should be constant for the whole circle, not dependent on time. Okay, but what if, okay, we want to skip a few steps. We don't exactly want to make the unit tangent vector. Well, we have a formula for that. Okay, again, it involves magnitudes, okay, but we've got the cross product of the first derivative and the second derivative divided by the first derivative cubed, magnitude of first derivative. This is the most commonly used curvature formula, and I think it's because we only have to take 2 derivatives. It does involve a little bit more of a cross product, but once you're kind of used to doing the cross product, that's a little bit easier than I think finding T of T. So this formula is nice because we don't need the tangent vector, and we don't need to take the derivative of it, or the unit tangent vector, excuse me. If you would like to see the proof for that, make sure you look at page 875 in your book. All right, so let's try using this formula for this next example. All right, and I'll try to leave it there at the top, just so we know. Okay. All right, we're gonna find the curvature at a specific time. And that specific time is important because now we're dealing with something that's not a circle. So the curvature could change with respect to time. All right, so first things first, I'm just gonna start taking derivatives. So my first derivative of the vector r will be 2t plus 2t squared plus 2. That's a lot of 2's. That means that r prime of 1, because remember, I'm not going to cross the vectors in general if I've got a specific time. Let's plug in values as we go along, because later when I need to take the cross product, I definitely don't want it to be with functions. That seems a bit more tedious. All right, so my the first derivative of the vector function at 1 is 2, 2, 2. I think, why did I write a plus here? Sorry, there we go. Okay, but if I want to do the second derivative, I need to do it in general first before I evaluate it at 1. So I will again get 2. Oh man, I see that I've been making a couple mistakes. Sometimes it gets confusing going from writing it as a linear combination to a vector form. So make sure you just choose one and try to be consistent. Okay, 2, 4t, and 0. That means that the second derivative of the vector function evaluated at 1 will be 2, 4, 0. Okay, and now the one other thing we might need, we want to do ahead of the cross product, is finding the magnitude of the first derivative vector at 1. And that was this function up here. So the square root of 4 plus 4 plus 4, okay, which is the square root of 12, which maybe you'd like to simplify to the square root of, or 2 square root of 3, but that's kind of up to you. All right. Now, the last thing we need before we start plugging stuff into our formula is we need that cross product. So I am going to do r prime of 1 cross r double prime at 1. And eventually, don't forget, we're going to need to take the magnitude of this. But first, I, j, k. And order matters. Order matters, people. I saw that on some of our quizzes this past week. 2, 2, 2, and then 2, 4, 0. Okay. All right. And I would definitely get in the habit of trying to write it in linear combination form, because I also saw some people mess up. They forgot that j had to be negative. So first term, 2 times 0 minus 2 times 4, which is 8. okay, that's the I component, minus j, okay, which will be 2 times 0, which is 0, minus 2 times 2, which is 4, plus the k component, which will be 2 times 4, which is 8, minus 2 times 2, which is 4. Okay, so now I can try to write it as a vector because I can see kind of where the sign should go. So this will be -8, +4, and +4. Okay, so that is our derivatives evaluated at 1 crossed. I need the magnitude of this. So the magnitude of r prime of 1 cross r double prime of 1 is the square root, sorry I'm writing kind of crooked here, of 64 plus 16 plus 16. Okay, that will be, well, this will be 32, so together that'll be 96. Okay, which I can simplify a little bit. 4 root 6. Whew. Okay, now we're almost there. Now we just gotta plug it in. So let me use a different color to plug in. Let's look back at our formula up here. I need to put the magnitude of what I just found over the magnitude of the first derivative cubed. Okay, so my curvature is going to be 4 root 6 divided by magnitude of this vector, so 2 root 3. Okay, and maybe I should use some better notation because this won't be consistent for the whole curve. So I'm going to say curvature when t equals 1. All right. Oh, and I forgot, this needs to be cubed. Okay, so you could leave it there, all right, but maybe it's multiple choice. Maybe you want to simplify a little bit. I'll get 4 root 6 over 8 root of 27. So I could divide that. I could get root 6 over 2 root 27. Okay, maybe root 6 over 6 root 3. Okay, then finally, if you really want to take it one more step, root 2 over 6. It's a nice rationalized answer for all those who like rationalizing. So curvature of this curve when t equals 1, excuse me, this curve right here when t equals 1 is root 2 over 6. And notice, even though this was some work, we didn't have to find the unit tangent vector. So if we haven't already found the unit tangent vector or the problem doesn't ask for this, this is kind of a much nicer option. It just involves taking some derivatives. Okay. All right. There is another example on the next page. Okay, but let me scoot that down. I am going to let you guys fill that one in on the notes yourself. Make sure you check your work. I will have the answer posted. And so finally, there is one more formula for curvature. These are definitely formulas you want to put on your note card. But this is for plane curves. Okay, y equals f of x. Okay, so curves kind of in that y equals yx plane when we're dealing with just functions. So I've got the magnitude of the second derivative divided by 1 plus the first derivative squared to the 3 halves. Okay, this kind of looks like our arc length formula. Remember that from long ago, BC. Kind of looks like our arc length formula. So let's see how this might work. Okay, why would this be easier? Well, notice that we don't have this is not parameterized in terms of t anymore. So if I'm given a function where I don't have any t's, I don't have more than one component, maybe this is our best option. So the first thing I want to do is I'm going to need my first derivative. So y prime is going to be cosine of x. Okay, and then I'll need my second derivative. So y double prime will be a negative sine of x. Oops, that's t, x. Okay, put it all together. Curvature will be, and this is, since these aren't vectors, this is actually absolute value. So absolute value of negative sine of x over absolute value of 1 plus cosine squared of x to the 3/2. Okay, and other than taking out that negative in the numerator, it doesn't really get much simpler. So this is definitely a formula you would use if we were really wanted to evaluate at a point, okay, for this curve. Okay, so let's do this last example because it asks us to do a little bit more than just finding the curvature in general or at some point. We will want to find the curvature first. So what we do want to do is we want to find the center of the circle of curvatures. So if you think back to the other section of notes here, this is our circle of curvature, kind of that, if we calculate the curvature right here, that will be the opposite of that radius, or the reciprocal of the radius will be this distance right here. Okay, so we're looking for this circle. We're looking for the center for the curve y equals x squared at the point 1, 1. All right, well, first, I'm gonna need to find the radius of this circle because this is not the center. This is the point on this curve, and we want to show, let's kind of sketch this out first. Okay, if I've got my XY plane, and if I've got my parabola here, okay, and the point 1, 1 right here, okay, I'm trying to find, this is not gonna be very accurate, but actually it's not a bad circle, but not accurate very much. I'm trying to find where the center of this circle is, where this kind of matches the curvature at that point. Okay, so remember that I want to find the radius of the circle first, because if I can find the radius of the circle, I can use the distance formula from this point to the center, and then I can find that. So my radius will be 1 over the curvature. So I'm going to need to calculate the curvature. All right, well, I've got y equals x squared, and my first derivative will be 2x. My second derivative will be 2, which is convenient. Okay, so the curvature at any time x, or any x value, remember, is this formula up here at the top. Put the absolute value. I know you can hear that squeaky toy in the background. Sorry. Absolute value of 2 divided by the absolute value of 1 plus the first derivative squared, all raised to the 3/2. So then when I plug in the x value 1 from our point, I'll get that the curvature at 1 will be 2 over absolute value of 1 plus 2 squared to the 3/2. Okay, so this will be 2 over 5 to the 3/2, which you can leave that way, or you can think about it as 2 over 5√5, up to you. We do want this radius though, so radius will be 1 over 2 over 5√5, so we will get 5√5 over 2 as our, sorry, this pen is kind of drying, as our radius. Okay, from there, all right, we still want to find the center of the circle where this is the curvature. So we're looking for this, the center of this circle right here. All right, I'm gonna give myself more room on the back. Okay, so you go to a new pen too. Given that our radius is 5√5 over 2, and we know that a point on the curve and on the circle is 1, 1, we could use the distance formula to find the distance from this to the center, some x, y, and the distance between this point and this, if this is on the circle and this is the center of the circle, should be the radius. Okay, so we're going to use the distance formula, which will tell me that 5√5 over 2 should be equal to the square root of x minus 1 squared plus y minus 1 squared. All right, well, let's square that just to get rid of that. I will get 125 over 4 equals x minus 1 squared plus y minus 1 squared. Okay, now remember, 1, 1 is not the center of our circle. It's the point that's on the curve. We need x, y. And if we have 2 unknowns, we need 2 equations to solve that. So we're gonna need another equation. All right, well, other option, okay? We can make, using this circle, and let's say that this is the center of that circle, we can make a line through these 2 points, right? Okay, so we can make a line through those 2 points, and that could be our second equation. So we could make a system of equations. Okay, so line through 2 points. Okay, well, we know that it also, okay, so remember, let me just think about this first. It's going to be y minus 1 equals some slope times x minus 1. Because 1, 1 will be on the line, but so will be the center xy. And so this xy should be the same as this xy. All right, but I need my slope. Well, if we think about it intuitively, okay, we can think about this line, okay? If it's a secant line, it should be perpendicular to the tangent line of that curve, okay, at that point. So those should be perpendicular. Okay, well, you're like, shoot, Miss Kelly, do I have to find the tangent vector? No, no, no. Don't forget, back to BC calculus, I can find the slope of the tangent line if I just take the derivative. So I can find the slope that I want by taking the derivative, okay? If y equals x squared, y prime equals 2x. The point I want the derivative at, y prime of 1, is 2 times 1. Okay, so the tangent slope is 2. If this line is going to be perpendicular to the tangent line, I want the opposite reciprocal slope. So that means this should have negative 1/2 slope. Okay, now that we have this, let me solve this a little bit. Okay, so I'm going to get y equals negative 1/2 x, then I'm going to have plus 1/2, okay, plus another half, so plus 3/2. I can sub that into this equation right there. So I'll have that 125 over 4 will be equal to, and I'm going to want to FOIL this out because I'm going to want to solve for x. So, all right, x squared minus 2x plus 1 plus, ooh, here's where it's going to get fun, negative 1/2 x, so minus 1 plus 3/2, so plus 1/2 squared. Okay, that's going to be x squared minus 2x plus 1 plus 1/4 x squared, then 2 times 1/4, so minus 1/2 x plus 1/4. That's 125 over 4. Okay, I want to get rid of these denominators. I'm just going to multiply everything by 4. So I'm going to get 125 equals 4x squared minus 8x plus 4 plus x squared minus 2x plus 1. That'll make it a lot easier for me to combine like terms. You don't have to do that if you like fractions, but I think that makes it easier for me to visualize. All right, all together, without moving anything, I've got 125 equals 5x squared minus 10x, and then plus 5. So if I set this all equal to, ooh, that would be nice. I could divide everything by 5. Okay, so I could get 25 equals x squared minus 2x plus 1. So I'll get 0 equals x squared minus 2x minus 24. which is a lot easier to factor. I will get x plus 4 and x minus 6. So which of these is the one that I want? Because remember, we're trying to solve for the center of a circle. X equals -4 or x equals 6. And this is where we want to go back and look at our diagram, which you can kind of see under here. X equals -4 or x equals 6. Okay, well, the circle has to go with the curve. So, wow, this is a very inaccurate circle if we think about it, but the point 1, 1 is on the curve. X equals 6 would be all the way out here. Okay, so it can't, the circle, if it's supposed to go curve with the function we're looking at, the circle couldn't be over here. That would curve against the curve we're looking at. So it has to be x equals -4. Okay, so it's got to be this one. Okay, so that is our x value. Now we need to find our y value. We're so close, guys. So I can choose to plug this back into one of my equations. I think this one might be a little nicer, maybe. Okay, so I am going to use my point slope equation. All right, and I'm going to say y minus 1 equals -1/2 times, now I know, -4 minus 1. Y minus 1 equals -1/2 times -5. So I've got 5/2 plus 1, which is 7/2. So last but not least, the center of my circle of curvature for y equals x squared at the point 1, 1. Okay, the center of the circle of curvature is -4, 7/2. And that took a little bit of work, but we did it.